All right. Hello, Stacey. One thing that I wanted to let us know is that before you watch this screencast, you want to be already have watched the screencasts and have good clarity of mind about the double slit interference that we did back in topic 4, and we kind of proved those original proofs with double slit and d sine theta and all of that. And you also should be really good at single slit and the patterns it created with a single slit interference. And you should have both of those sort of like in the pocket already good before you even watch this video. So if that's not the case, then go watch those other ones and study a little bit more before you come to this one. Anyway, here we go. We're going to look at double slit and single slit when they come together, when you have both of them at the same time. And so when we had double slit, let's remind ourselves that we had two openings that could create a constructive interference if this path length and this path length were different by exactly an integer amount. We could end up getting a bright spot right here, and that's being shown by this peak, but that this is bright right here, and then dark, and then bright. And we had this an equation that we would use in SL. And we also had one d sine theta, right, equal to m lambda. So that was another one that we could use. But in any case, here we have our new, we've taken out this middle section, and we saw how that creates the possibility for rays of light from here and halfway down, half of this, to meet and be destructive at this location. And so that's if you have a single opening. And to keep them clear, we have a couple things. We call this one diffraction, even though actually there's some interference happening. We refer to this as diffraction and refer to this as interference, even though this obviously has some diffraction coming out of each of the two openings. But we refer to this as diffraction, and we use B, and refer to this as interference, and we use D. And why this video is so important and tricky is that we have both D and B when actually we have a true double slit, because here we have D equal to B, and we're looking at the comparisons between them. But the reality is that D can never be B in a single experiment. If you look at a single experiment, you know, you've got D's and B's that are going to be different than each other, because the gap between two openings obviously is going to be bigger than the gap of an opening. And you have both at the same time. You're going to have single slit and double slit all happening at the same time whenever you have double slit. So you can see these double slit peaks that are happening, but then you see them getting like cut off because of what's happening with the single slit envelope that is occurring. So we see this sort of overlaid pattern of both of them. To help actually see this, let's see if I can get this little video to work. Hopefully it'll work nicely.
So I'm going to show how double slit and single slit relate to each other. So we have a laser here. It's a very bright green laser. And then what I have here is many different possible number of slits. So example, 2 slits, 1 slit, multiple slit, many different things here. And when I shine the laser through, you'll see a pattern over there. So that's what we're going to do. So I put it into this holder just so it stays firm. And then I'm going to shine my laser through, and you see the pattern on the wall. So let's take a look at what this pattern is. So go ahead and walk up right next to it. And we keep getting even closer, 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 closer. So this is a double slit pattern, and you're seeing the single slit envelope, which is really interesting. If I show you just the single slit that has exactly the same sizes, you see there isn't the extra little fringes. This is just the diffraction pattern, right? But when I go back here, and now you can see all the tiny fringes. Okay, there we go. Awesome.
All right, hopefully that helped a little bit. And the idea here is that when you have these D that's bigger than B, that you do get this envelope that was encapsulating them. I did take a zoomed in picture of those. So let's take a look and compare those, because I know it's hard to see on the video. So this is a double slit that has a D value that's the same as a B value for a different setup. So it's, if you can look here at these setups, you can see this is for double slit, and they have various types of double slits, and each one has different varying spacing between the slits and how big the slits are themselves. And that's what these numbers down here are representing. But if we look at the fact that the single slit envelope, that here we're seeing just a single slit, and that's with 0.04 being our single slit. And you can see that the single slit, 0.04, creates this envelope. But then if I do a double slit that has a 0.25 separation, but that the single slit is still 0.04, we still get this 0.04 created single slit envelope. See how that basic shape matches this one. So you have that what's called single slit envelope. But within that, you have all these little tiny bright ones. You can see little tiny bright ones right there. Those are happening because of the double slit. That's related to D and the fact that you have this 0.256. And you'd go, okay, wait a minute. That means that D is bigger because this 0.04 is technically what we would call B. I wasn't making a distinction when they were equal, but now we got to start being really careful. This 0.04 we're going to call B, and this 0.25 we're going to call D, and D always is going to be bigger. Okay, D is always going to be bigger. And that's why these are so tiny. If you recall, when we were doing the double slit, we knew that if you had the separation D get bigger, then the double slit pattern would get smaller. So since D is always bigger than B, we're going to see that we're always getting multiple little bumps there, and those are inside the envelope. Now I'm going to show you a way that it often gets graphed. So here you're seeing this single slit envelope that isn't being shown on this particular graph, but you get a sense of it because here we go, and here's this bump, and here's the big central one, and then here's the smaller, the secondary ones. So we see here's the big central one, dies off here, we get this cutoff, and then it reappears again in the diffraction pattern, remember. And these don't match because this is only like 1, 2, 3, 4, 5 maybe double slit bumps inside the single slit, where here we have like 6 or something. But the idea is shown nicely here, where these bumps are these bumps in the secondary part of our single slit envelope. Okay, and so let's take a look at what actually happens there with the math. If we look at this one with the actual math, where you have 0.25 and 0.04, we would expect there to be, that's about divisible by 6, right? That's about a 6 ratio, 0.24 divided by 6 would be 0.04. So we would expect from the center of this bright, if this is the slot that I used, this far left one, which was the one I used, then we would expect there to be 6 bright spots here. 1, 2, 3, 4, 5, 6, and there are 6 bright spots going off here. And why is that? That's because the ratio of D to B here will have the same ratio as this B to D ratio here. So this one doesn't exactly match the one I just did, but in the one I just did, I'll come back, with this one, we had a D that was 6 times bigger than the B, which is why from the middle of the single slit envelope over to the cutoff, we're seeing 6 double slit bumps when you see this here, right? And this graph matches a different setup because there's less. With this graph, you've got your 1, 2, 3, 4 instead of 6 bumps. So the ratio of D to B with this particular graph would be 4. So what's interesting with that is if we think about the equations that are going with each of these. So think about what an IB question could be. What would they do to us here? So let's say they had this graph, and notice that it's in 10 to the negative third radians, so thousandths of a radians. And this would be theta, right? We'd be thinking of those thetas from our various proofs. And on this graph, you can get the theta that refers to the double slit. That theta is going to be, remember that that's the double slit, so that's going to be this tiny little distance theta from bump to bump. And if they've given more marks here, hopefully, you could actually figure out what theta is, right, that relates to this equation. Now, I wish they used a different Greek letter for this theta, because over here we have the single slit envelope and they're using theta again. It'd be nice instead of theta here, they used, I don't know, alpha or something. But in any case, think of this as the other theta. This is the one with the single slit. And this theta is going to be defined like we did with single slit from the peak going over to the first cutoff. So we go from the single slit to the cutoff, which is right here, right? And that envelope is seen nicely back in this slide. So I'm going to jump because they show this dotted line that's showing that envelope, right? And then just to remind you, we can see it here actually. Here's the cutoff. It gets brighter, 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 cuts off. And that's being shown here because the vertical axis is, right, intensity. So what equations we're going to use depend on which theta we're picking. So if we're looking at the double slit here, we want to make sure we're using this interference double slit where we use D because D is the distance between the openings. And if we're using this equation, then the theta we're talking about is for the single slit envelope. And we want to be very careful to go from the peak, the middle of the large middle bright spot for single slit to get over to the cutoff point there. That's a lot. We would definitely want to do some examples with this and see how it goes, but I would come back and watch this video after you've done some problems because maybe some of the things I said were clear. I think I might have mixed up D and B once, but hopefully you're clear right now that D is always supposed to be the distance between the two slits, where B is actually the opening of one of the slits. And this pattern that we get relates to both the B and the D. I'll go ahead and cut off one question that often gets asked, and that is, well, if there's a single slit envelope from this one, shouldn't there be a different single slit envelope from this other one? That often gets asked because if you look back, we only have one single slit envelope. So, you know, is that from this one or is that from that one? And that's the whole point. That's the beauty of this, that this single slit envelope is actually from both of them. And the fact that they are slightly different is what's creating the double slit peaks here that are inside of it. So that's exactly what you want to be thinking about, and how this double slit thing that's occurring is because there are two single slit patterns. And the math there, if you were trying to prove that, is actually quite complicated. Luckily, we don't have to do that. We just need to really make sure we understand the relationship between B and D and how that leads to these different patterns when we have a actual double slit pattern to look at, as we did here. Anyway, I hope that helped, and try to keep your stress levels down as we're doing this, and have some fun learning some physics. And don't freak out and worry about the deadlines. It'll all come together. Work hard, keep learning, and have fun. So hope I can see you in person soon. Good luck. Thank you.